This clock is fully parametric. Change one value and the entire design updates. In Fusion, I'll show you how to build it, how to fix constrained sketches when things break, how long it actually takes to 3D print at different settings, and what it would cost to have this manufactured instead of printing it yourself. Create a new component first. Clean structure makes everything easier later. Use the S key to open design shortcuts and search for parameters. Menus are useful when you're learning, but shortcuts are faster and let you find tools you might already recognize from other CAD programs. We start this design with a small set of user parameters: the diameter, the depth, the movement mechanism, and the shaft that belongs to that movement. The movement machine and shaft are not 3D printed, but the model needs to make space for them. It's good practice to think through your parameters in advance, but you can always come back and add more later. And in this project, we will. For faster data entry, leave your mouse near the plus button and use the tab key to move between input fields. Press enter to confirm and close the dialog when you're done. Use design shortcuts to create a new sketch on the construction plane facing you. Press C to create a circle, start from the central point at the origin, and set the diameter using your clock diameter parameter. Next, press O to offset this circle. We want the outer diameter to update automatically when the clock diameter changes, so use a simple formula instead of a fixed value. In this example, I offset the circle by 0.08 times the clock diameter. With a diameter of 175, that gives us an offset of 14. Now, if we update the clock diameter, the outer diameter updates as well. This keeps the design fully parametric and easy to adjust later. Press C to create a circle for the shaft as well. When designing a real clock, leave a bit of room for tolerances and expect to iterate. It usually takes a few design and print adjustments before the fit is right. Press R and oversketch a 2-point rectangle starting from the origin. Creating the rectangle first makes it easier to add formulas when referencing other dimensions. Press D to activate dimensions. For this dimension, use a formula that captures both the offset circle diameter and the clock diameter. Then divide the result by 2 since we only need the radius length, not the full diameter, for a 2-point rectangle. For the second dimension, there's no need to repeat the formula, simply reference the dimension you just created. This saves time and reduces the risk of errors by keeping the setup simple. You now have the sketch for the foot. Next, we'll create the index marker. Open Design Shortcuts and choose the center rectangle. This rectangle type works well here because it makes alignment to the center of the design straightforward. Set the height to slightly more than 10% of the clock diameter. For the width, use a fixed value. This means the length updates when the clock diameter changes, while the width stays fixed at 3 mm. We'll run into a few issues around this setup and fix them near the end of the tutorial, but for now, we'll keep moving. Finally, add a dimension that controls the distance from the center of the clock. This dimension should also update with the clock diameter. In this example, I set it to slightly more than 40% of the full clock diameter. If you have trouble selecting the right object in a crowded sketch or when geometry sits behind other objects, press and hold the left mouse button. This opens a pop-up menu showing all available selection options at that location. Jump straight into the Extrude command by pressing E. There's no need to close the sketch first. Small habits like this save time and they add up fast over longer projects. Select the clock geometry, including the index marker, but leave out the symbolic hole for the shaft when you extrude using your depth parameter. After the extrude, the sketch visibility is hidden automatically. Go back to the browser and turn the sketch on again so you can continue with the remaining extrude operations. Make sure your next extrude is set to new body. This gives you the flexibility of individual bodies, which is especially useful for multicolor 3D printing and later design changes. While the operation is often set to new body by default, always pay attention. When you create geometry next to existing bodies, Fusion will often suggest join instead. That small change can merge bodies unintentionally, so make it a habit to double-check the operation type before confirming the extrude. Give the front a formula if you want the depth to update automatically when you change the clock diameter. Add a minus sign in front of the value, since this extrude runs in the opposite direction of the default extrude direction. Before confirming, change the operation type back to new body, since Fusion switches it to join as expected when working next to existing bodies. This keeps, as mentioned earlier, the front as an independent body for later adjustments in Fusion and for multicolor control in your 3D printing slicer. This sketch on the back creates space for the movement mechanism, and these dimensions should stay fixed even when you change the overall clock size. Because of that, use fixed values instead of formulas here. From a manufacturing perspective, you can't bridge a span this wide if you 3D print the clock with this side facing down. There are a few ways to work around that. One option is to print a separate insert with a small bridge that fits inside this rectangular opening, allowing the main body to print cleanly without support. For design purposes, create a projected sketch from the shaft hole and offset it slightly to allow for manufacturing tolerances. You'll almost certainly need to print and test this to find the right fit. To save time and filament, do that testing on a small standalone part instead of printing the entire clock. Extrude this feature so it references the clock's depth by extruding to the body, then add a small distance in the formula so the symbolic shaft stands slightly proud of the clock surface. If you plan to design and 3D print the minute and hour hands as well, reverse engineer the shaft geometry so the hands fit correctly onto it. Great job keeping up. Now is a good time to save the project before you move on. Next, we'll extrude the index marker, start the extrude command, select the index profile and set the operation to new body. Before you confirm, double check that the operation hasn't switched back to join. We'll pattern this part later, so here's a time-saving move. Apply the appearance now, before you create the pattern. That way, every body created by the pattern inherits the same appearance automatically and you avoid redoing the styling work. If you're using custom appearances, rename them. It makes it much easier to stay organized once your design starts to grow. And if you need RGB or HTML color code ideas, there are plenty of great sources online, including AI tools. For reference, the keyboard shortcut for appearances is A. Now continue by opening Design Shortcuts and selecting Circular Pattern. Use the View cube to change the view so selection is easier. Select the index body as the object and use the green axis as the pattern axis. Set the quantity to 12 and confirm the pattern. With all 12 index markers in place, activate the top-level component. Create a new component, then use the Tab key to jump directly to the naming field. Name the activated component Hour Hand and confirm. In situations like this, it's often easier to come in at a slight angle when selecting the sketch face. That makes it much clearer which face you're working on and reduces the risk of picking the wrong one. There are several slot commands available. The center-to-center slot is a good choice here, since it lets you define the slot by sketching its endpoints directly. When you add the dimensions, include the clock diameter in the formula. That way, the sketch updates automatically when the clock diameter changes. At this point, the setup is theoretically correct, but the sketch is not fully constrained. That will cause some issues later on, which we'll fix toward the end of the tutorial. I've intentionally left this in the recording because this is a very common situation to run into. For the width, I'm suggesting a fixed value here. If you prefer, you can also make it parametric using the same design principles we applied earlier in the tutorial. As a design choice, I'm also using a fixed depth. This gives direct control over the feature depth and keeps it aligned with dimensions that work well for common nozzle sizes and typical 3D printing settings. With the hour hand in place, repeat the same workflow. Create a new component and name it. Continue with the bottom-up design approach and sketch the minute hand directly on top of the hour hand component. Use the center-to-center slot again, but update the formula and change the fixed width value. The math here is very simple. If formulas feel unfamiliar at first, don't worry. You'll get comfortable with them quickly. Just like before, go straight from the sketch into the extrude command. This keeps the timeline clean and avoids unnecessary steps. Set a fixed depth of 1.5 millimeters. A fixed depth gives you predictable results for 3D printing and helps avoid weak or overly thin features. It's time to fillet the edges. This improves the visual quality, the tactile feel, and in some design scenarios, overall strength. Before you start, activate the clock component. This ensures the fillet is recorded in the correct component and keeps the design structure clean. Add a simple, discrete fillet to the inner circle. In the fillet options, choose the tangency setting and set it to G1. G1 tangency means the fillet is tangent to the adjacent faces. In practical terms, this gives you a smooth visual transition without forcing curvature continuity. The surfaces meet cleanly, but the curvature itself is allowed to change at the transition. This makes G1 fillets predictable, stable, and well suited for mechanical parts and 3D printing. Higher tangency levels focus more on aesthetic surface flow, but G1 is often the right balance between simplicity, robustness, and manufacturability. It's soon time to test the parametric setup and fix a few small issues, but before that, I'll fast forward a bit here to save you some time while adding the final appearances. One thing worth mentioning is that you can duplicate appearances to quickly reuse the same material type. This is much faster than starting from scratch each time. It's also a good idea to rename your appearances. When materials look similar, clear names make it easy to identify the right one just by hovering over them. This is also a good point to adjust a few settings to better present the model. You can change the visual style to get a cleaner look, turn off the origin to reduce visual clutter and make the design easier to read. Before updating any parameters, save a new version with a clear description. That way you have a clean reference point and can always roll back if something breaks when the parameters update. Moment of truth. Let's test this. When we scale the clock down, the hour and minute hands don't follow, so something is clearly off. To debug this, the different colors assigned to the components are visible in the timeline, which makes it easy to locate the correct sketches. When you open the sketch, you can see the problem immediately. The sketch isn't constrained, so it doesn't respond properly when the main dimensions change. To fix this efficiently, add a user parameter for the hour hand that references the clock diameter. This ties the hand length directly to the overall size of the clock and restores the design intent. We'll assume the minute hand has the same issue. Add a corresponding custom user parameter for the minute hand component as well. Once both parameters are in place, the hands will scale correctly when the clock diameter changes. Switch to the correct components and update the sketches using your new user parameters. Small mistake on my end when I updated the hour hand. I should have constrained that sketch. In this case, adding the parameter is enough to fix the behavior, but it's still better practice to fully constrain it so it won't drift later. With both parameters in place, let's update the model again. When we change the clock diameter from 175 mm to 100 mm, the hands update as intended, but a new issue shows up. The index marker has drifted to the right, and this is the consequence of leaving that sketch under constraint. The troubleshooting approach here is slightly different. The good news is it's easy to locate the problem sketch, because we captured so much information in the original sketch. Draw a line through the center of the rectangle. With the line selected, press X on the keyboard to convert it into a construction line. You'll see it change to a dashed style. This means it won't be part of the final geometry, but it can still be used to control the sketch. Now, apply a collinear constraint so the rectangle aligns with this construction line. Pick the guiding line first. As soon as the constraint is applied, the sketch turns black, which tells us the sketch is now fully constrained. Two final tests confirm the model works as intended. By changing a single user parameter, we can scale the entire clock up or down without breaking the design. From a business perspective, this means one design can cover multiple product sizes without extra modeling work. Next, we look at different 3D printing setups and how size affects print time. We're now in Prusa Slicer, setting up the print on the original Prusa i3 MK3S Plus. For simplicity, we're only looking at the main body with the hour and minute hand markers, since the print time for the hands themselves is negligible. The part is oriented with the back facing down. Because the central opening is too wide to bridge reliably, you'll need either to place something in the middle or print a separate insert. If you're printing multiple copies, reusing a small insert for that opening can save a significant amount of time since you avoid printing supports for that area on every run. I sliced this model using 4 different profiles: 0.10 mm layer height for detail, 0.20 mm quality, 0.30 mm draft, and 0.30 mm draft with ironing for a smoother top surface. You can fine-tune the print in several ways, for example by reducing infill, but the print times still tell the same story. Even at coarser settings, this is a long print. With the detail profile, it exceeds 40 hours. And that's the theoretical best case. In reality, some prints will fail, so the expected average printing time is higher than what the slicer reports. I also looked up some online quotes for manufacturing this in black PLA. Pricing starts at around $120 for a single unit, drops to about $60 for 10 units, and only slightly further to $58 for 50 units. That tells a very different pricing story compared to processes like laser cutting sheet metal, where unit cost drops significantly at higher volumes. This is interesting because it highlights how 3D printing remains time-driven rather than setup-driven, which directly affects scalability and margin planning. If you found this useful, hit like or subscribe. Drop a comment below with your thoughts on the workflow. Visit the Maker Letters for written guides, tools, deals, and more. See you in the next video. Thank you.